Hello, everyone, and welcome. This is a very odd position in which to speak, but anyway, thank you all for being here. It's almost the end of 2 incredibly busy days. I don't know, my brain is totally about to blow up, but I'm very grateful you came to my presentation. It's a talk that I wanted to give for a very long time, and then turns out that this is literally the only venue that will accept talk about how things work inside Kafka. So here we are. I wanted to share that because Kafka is even more useful than we think, and there is a poorly documented but really nice general purpose protocol inside of Kafka that I think will be awesome if more people knew about and used. So I'm glad that you're all interested in learning about it and maybe using it. Just for a quick show of hands, how many of you know Kafka? Like if I say you have topics and partitions and I produce and consume, good chunk of you. Okay, so I'll go pretty quickly about the parts that, what is Kafka, and then start diving into the details, so bear with me. So we'll start with a very, very brief Kafka 101. And then we'll start talking about the consumer protocol and what were the requirements and why did we design it the way we did. 3 different times, by the way. And then I'll go into the implementation and like how the protocol itself works. And then I'll go through 3 examples of how we use this protocol for things that have absolutely nothing to do or very little to do with Kafka consumers. So that's the idea. About me, I'm not actually a small bird, but this is a book that I wrote. I currently work for a company called Confluent, and since I had to say it a lot the last 2 days, we do not do wikis. We are a company founded by the people who invented Apache Kafka for LinkedIn, left, built a company, we maintain Kafka, we add new features, we sell Kafka support. We also have a bunch of other stuff that should make it easier for you to use Kafka. And so let's talk about Kafka. Come on. Okay. I think I'll just, since I'm stuck here anyway by a bunch of barriers, I may as well just use a keyboard. So what is Kafka? Well, the way we sometimes describe Kafka is a streaming platform. What does streaming platform mean? It means that you take events, you publish them, Kafka stores them as nicely ordered streams of events, you can subscribe to those events and consume them, and then we have things like connectors that allows you to generate those events from something like a database, or to send those events to something like a database, and we have stream processing modules that lets you read a stream, do stuff to it, and write a new one. The Kafka cluster itself at the core is a glorified storage mechanism. We sometimes say that it's a message queue that married a file system. So that's one way to look at it. At the very core of Kafka, we have the idea of partitions. Sometimes we call them logs. There is a book, I Love Logs, that explains that a log, basically an ordered set of stuff that happened, is the basic abstraction of most of data management. So if you have databases, they kind of are based on those redo logs, and Kafka takes it to be a first-order construct. So if you publish events into a topic, they get stored into a bunch of those partitions. Partition is the unit of scalability of a topic. So a topic will have a lot of partitions. They will be stored on all different kinds of servers, and you will produce and consume events with those partitions. And each one of those partitions is well-ordered. Preserving order is the one job that Kafka really tries hard to do very well. And there is sequence numbers, also called offsets, to every message in a partition. Now, every partition is replicated 3 times because it's a distributed system, and machines can go poof and disappear on us. So one of the partitions is a leader, and we basically always produce events to the leader replica. Sorry, not one of the partitions. One of the replicas of a partition is a leader. We produce events to the leader replica. We consume events from the leader replica. We do that because that's the easiest way to maintain consistency. And remember that consistency is the one thing that Kafka tries to do really, really well. And then the replicas live on separate brokers, and if something bad happens, we count on one of the other replicas. The replicas have one job, remember, the leader handles all produce and consumes. The replicas, all they have to do is keep copying events from the leader and try to keep up. If something happens to the leader, we basically choose another one of those replicas as the new leader and starts producing and consuming there, and hope that we did not lose any message on the way. We don't have to hope, we have guarantees. That's a totally different talk. Now, if we look at how we consume events, consumers basically start reading, hopefully from the beginning of a topic that they're interested in, and they kind of move forward, continuing to read stuff. After a while, they reach a state that they are happy with, and they store their current position in what we call a consumer offset topic. So the consumer says, okay, I read up to event number 7 on partition 0, and I've read up to event number 4 on partition 1. Please keep it for me. And then if something happens to the consumer, if I crash, for example, and need to figure out where to start again, I start from the last saves to offset. The whole offset management thing is incredibly, it looks simple. It was actually a bit more sophisticated than that. It's a fascinating topic in its own right. I'll have a list of references at the end, and you can find a different presentation that tells you all about offsets. Now, one of the cool things about Kafka, and arguably the reason that it's really took off in popularity, is that you can have really large number of consumers. 50,000 is not unheard of, and each one of them will manage its own position in the queue. So they are totally independent and unrelated to each other. And look at how little information you really need in order to maintain a consumer. This is basically what allows Kafka to have a lot of consumers, while other pub/sub-like messaging systems try to keep a lot more state and therefore have a lot more issues in memory allocation as the number of consumers grow. Now, I made it sound like there is just one consumer for all the partitions, at least for a certain topic. This is 100% incorrect. So if you have one consumer and you start and say, I'm interested in events from the clicks topic, you'll start getting all clicks. But at any reasonably sized website, at some point, one consumer will not really be able to handle all those clicks. If you add more consumers to the same consumer group, which you define with a group ID, they'll basically kind of figure it out and say, okay, I'm reading those partitions, you're reading those other partitions, and just kind of balance between them. They will still commit offsets to the exact same partition, because just imagine there is if a world in which there's a lot of consumer groups, you don't want to look through all the states of every single consumer group in Kafka in order to know what you're supposed to read next. So having a single partition with everything that goes on in the consumer group basically lets everyone find its state relatively easily. Now, one of the things you get with the consumer group is that if a consumer crashes, we detect that, and the other consumers can basically keep on reading the same partitions. So you have automated failover, you don't get orphan partitions, and this scales as long as you have extra partitions. And then if you try to add more consumers than you have partitions, you'll have what we sometimes call unemployed consumers. They have no partitions to read from. All this is fairly simple. The rest of the presentation will go into the excruciating details of how consumer groups really work. How do we discover that a new consumer just joined our group? How do we decide who is reading what? How do we detect that something went away and we need to rebalance? All those things are the topic of this presentation. Note that we wrote this protocol basically 3.5 times. We started with using Zookeeper. Zookeeper did not scale to the number of consumer groups or the number of consumers in the same group that we wanted, and we had a lot of trouble with that. We went and wrote a nice protocol, and then we decided that no, it's actually not good for a bunch of reasons that I'm going to explain in a second. And then we wrote one, we actually implemented it. The number 2 we discarded before we even started implementation, or at least shortly after we started implementation, but before it was merged. There may have been a branch. And then you have something, it goes live, people start using it. Immediately, people started complaining about certain properties having to do with hard bits. I'll talk about it. And then we basically, you kind of ignore all the complaints and say people are stupid, you don't understand us for like 6 months. And then after 6 months, it's like, okay, I don't know if people are stupid or my protocol is stupid, but I have to fix it because I can no longer take the complaints, basically. So here we are. So what are the requirements that we had when we started designing this protocol, basically immediately after we said that, okay, no more Zookeeper for managing consumer groups? The first is like the basics, right? If there's one job for consumer group, is that you have to allocate partitions when new consumers join the group, and you have to allocate consumers when something goes wrong and someone either fails or leaves the group. So the allocation of partitions to consumers in a dynamic way is the one thing that we knew we absolutely have to do. And then the second thing was the part that was actually a bit controversial. We decided that the partition assignment has to be done by the clients themselves, not by the brokers. Why is that? Because the second design after Zookeeper was basically let's have a broker make the decision. And then when we thought about it a bit more, we were like, well, first of all, we don't think it should be the broker, because that means that if I thought of an amazing new way to distribute partitions that works really well with my application, I won't really be able to use it until I convince someone to upgrade my broker or configure something on my broker or install something on the broker. Very often it's two totally different teams in an organization. Getting stuff done between those teams proved to be a much harder problem than we ever anticipated, basically. Like the hardest problem in computer science is getting two teams at the same company to work together, 100%. So we decided to totally bystep that by giving control to the clients. And then the concern was, do the clients know enough to make a good decision? Or do we need a centralized control just to enforce good decisions? And it turns out that the brokers don't really know anything that the clients don't already know. Actually, any attempt to enforce rules by the broker end up restricting the clients. For example, the first attempt was, oh, the brokers only will know if two clients are trying to consume the same partition, and we need to prevent that. But no, who says you have to prevent that? Maybe my application really wants to have some kind of standby, and I want two clients to consume the same partition. So the brokers basically don't know anything that I don't know in the clients, at least in the clients collectively. And therefore, the brokers are not qualified to make a decision, and they should not stand on the way. OK, so requirements 1 and 2 are done. And then requirements 3 and 4 basically came from very large users of Kafka, especially the LinkedIn team. They said, look, we have to support somewhere to the order of magnitude of 30,000 consumer groups, because that may or may not be what we're currently running in production. And we have to support consumer groups of the size of hundreds of consumers in a single group. Why? Because if you have a failover Kafka cluster and you have and it's really big and you have to copy everything from one Kafka cluster to another in real time, you need a very large consumer group to do it, because you're consuming every single partition on your Kafka cluster in a single group. So we needed to support those two things, no questions about it. And then the last one is obvious. It has to be consistent. Once there is an assignment, you're reading this partition, you're reading the other partition, you cannot just let anyone do whatever they want. They have to comply with the assignment. So what is the protocol really supposed to support? What are the operations? Well, you're supposed to be able to join the group, and then we wanted to elect a leader and have it assigned resources. Leader is any one of those clients. We wanted the consumers to have to maintain membership. That's how we detect if something goes wrong and we need to reallocate. They fail to maintain membership. And then you want to allow them somehow to leave the group nicely, so we wouldn't have to wait for them to just not ping us often enough. This is basically all the activities that I'll go over how we do. And the way it works, and I'm saying this now so it will be a bit easier for you to follow the protocol, we ended up with a 3-layer protocol, or at least 2-layer, and then one of them is kind of split. The basic protocol, the one that I'll start talking about, is the Kafka group membership protocol. It's responsible for who is a member in this group and who is a leader. And then there is the group protocol itself. It's the protocol that members of the consumer group use to basically decide on allocation. How do they communicate with each other? Remember, I said that all the information exists on the client, but it exists on the clients in a collective way. If you need to know what, but we need the leader who makes a decision to have all this collective information. You need a language for that. And this is the group protocol. And then inside that, there is a sub-protocol, which is the only part that is actually called a protocol, I think. And this is basically the assignment algorithm, like how do we assign partitions, and some extra metadata that may assist in that. So we'll talk through all that, and I'll point out on occasion which layer I'm talking about. So how are we using the protocol today? There is the consumer group membership, and I'll start by talking about how we do that, because that's the base use case. And then we use it on 3 other places. Kafka Connect uses the same protocol to basically take data copying tasks and assign them to different workers. Kafka Streams uses it to assign partitions to tasks to specific hosts that has specific state. And Schema Registry uses it for leader election. And those are the 3 use cases I'm going to talk about, 4 use cases I'll talk about in detail. So for the consumer group use case, who are we talking about? We are talking mostly about consumers who the only thing they want is to know which partitions to start consuming. And then on the broker side, we have coordinators. And any broker can be a coordinator. Every broker is a coordinator for a subset of the consumer groups, but every group only talks to a single coordinator at any given time. Otherwise, it will be very hard for them to communicate. So the coordinator facilitates the communication between the consumer groups. And therefore, if we are a consumer group, the first thing we have to start doing before we do anything else is find our coordinator. So luckily, there is a find coordinator request. So all of Kafka protocol is basically a request response protocol. So I'm going to, at every point when I'm talking about the protocol, I'll say what is the request, and then what is the response. The find coordinator request is the only request in this protocol that can go to any broker in the cluster. Everything else will go to the coordinator. And we basically say, hey, I'm a member of group X. Who is my coordinator? And we had to basically find a way that everyone who asks this question will get absolutely the same answer, but also that it will scale. So if I add and remove brokers, then I'll actually take that into account. What we ended up doing is basically say, hey, we already have this common offsets topic. It has a lot of partitions, so it's well distributed. It has replicas, so a single replica will always be alive for every one of those partitions, meaning that if I take the group ID, hash it, divide it by do modulo with the number of partitions in the offset topic, and I get a partition number 15. I find the leader will be a broker that is alive. This is the promise of a partition leader. I find a broker to talk to. And now I have a broker to talk to, and I no longer have to worry at all about offsets. So we use the same find coordinator protocol, even for things like schema registries that cares nothing at all about offsets. It's just a convenient convention. Anyway, the thing you get back is basically a URL, host, port, and security protocol, if it exists, of the broker you're supposed to talk to. So here is your coordinator, go. I found my coordinator. The next thing I want to do is send a join group. And now that's a lot of information. So I do a join group. The first thing is that I'm joining group X, right? And then I have to send a member ID. But I'm only now just joining the group for the first time. I don't have a member ID. So I'm sending an empty string. I'll get a member ID back. No worries. And then I want to say, what protocol am I talking in? This is the second layer protocol, the one that determines what is the resources that are actually getting assigned. So the resources that get assigned are consumers to partitions. So this is the consumer protocol. What algorithm do I support for assigning partitions? This can be a list. So let's say that I'm interested in range assignment or load balance assignment or sticky assignment. So I specify one of those, and then I can specify metadata. The basic metadata that members of the consumer protocol have to support is what kind of topics and partitions I'm interested in. So hey, I'm a member of the group X, and I want to read topic T. And range assignment is my favorite assignment algorithm. And everyone sends the same information. And the coordinator takes this information and responds to, first of all, if you were the first consumer to join the group, you are now the leader of that group. And we keep the members of the group in a nice linked list. So if the first one goes away, we know who the next one is and get a new leader. Note the O of 1 leader election because we have a single coordinator coordinating the entire thing. So we have the members, and so then when we know who the leader is, he gets the list of all the other members and all the metadata. Remember, the metadata is what topics are interested in. So you get member X member 1 is interested in topic T, member 2 is interested in topic T and topic T5. Like you just get all of that. And then everyone gets their own member ID. Now I have a member ID for everything else that I do. You get the protocols that we all decided that we're going to use. When I say protocol right now, I mean the range assignment protocol. And I'll talk about why we need to send this back in a second. The leader definitely have to know, but everyone else should know as well. And then we also tell everyone who is the leader. Sometimes this is useful. Now, about electing the assignment process, why this is really important. Everyone can specify a list of assignment processes in an order that they care about. And this is the way it works. So you basically, everyone says, hey, I'm round robin, I want to read round robin. And then the coordinator basically looks at all the protocols that everyone wants to talk in and says, okay, everyone agrees that they want to do round robin, so this is our candidate. And because it's the only candidate, it gets all the votes, so everyone is going to talk round robin. And the reason it's useful, and the first one I saw this entire thing, I'm like, oh my God, this is such over-engineering. When will I ever need that? Turns out to be incredibly important in upgrades. So you basically say, I prefer to talk sticky protocol because I have some improvements that I know will happen if I use the sticky protocol. But if somebody else insists on round robin, I support it. We didn't delete the old code yet. And everyone else basically says the same thing. Note the last one was not upgraded yet. So the last one does not support sticky yet. It will only support it after another upgrade, which means that right now the only language that everyone talks in is round robin. It's the only candidate. It gets all votes. But now I finished my upgrade. I bounced the last consumer. It's doing join group again. And as you'll see later, it means that everyone else has to do join group again. And that means that everyone now supports round robin and sticky. We have 2 candidates for the first time ever. Well, so note that how everyone specified sticky first. It means that sticky is the preferred protocol, which means that sticky now got a majority of the vote. So after everyone joins all the groups with this preference list, now the protocol that gets elected is sticky, and we just did a successful upgrade. I'm pointing it out because rumor has been that people don't actually know how to switch between 2 assignments in the same consumer group without taking everything down at the same time. Now you know you don't have to. If you learned nothing else useful from this presentation, it's how to switch to a new assignment protocol. So we got that. And next thing, now that we all know who is the leader and what protocol we're using, it's time to sync the group again. And now we get the assignment. And the whole reason for the 2 phase is to allow us to A, select a leader, and B, agree on a protocol. So that's the reason we actually have join group and sync group as 2 separate steps. So sync group, we basically send again, here's my group ID, here's my member ID, everyone sends that. If I'm the leader, in between those 2 calls, it was my job to decide which consumer is reading which partitions based on the protocol. So based on if it's supposed to be sticky, I try to keep whatever they previously had. If it's round robin, you get 1, you get 2, you get 3, you get 4, you get 5, you get 6, you get idea. If it's range, okay, you get 1 to 3, you get 4 to 6, you get 7 to 9. So you get the idea. The leader basically makes the assignment. Coordinator stores the assignment in Kafka. It has 2 good things. First, if the coordinator gets lost, we did not lose the assignment. And second, it means that if you want to kind of pick around and know what's going on as someone who monitors, you can just check in Kafka what's going on. Anyway, after it stores the assignment, it basically takes, for each member, it says, okay, you're reading those partitions, you're reading those partitions, you're reading those partitions, and that's about it. Woohoo! We have a working consumer group. Consumers know what to consume. They can start consuming messages. Pretty much by this point, you have a working consumer group. You can see that this is 2 round trips, so you don't want it to happen all too often. which means that we need a way for consumers to tell us they're still alive and keep hanging on to their existing partitions. Enter the heartbeat. And heartbeats are super simple. You basically say, I'm still alive, this is the group, this is my member ID, don't forget me, and if everything is okay, coordinator says everything is okay. I'll talk about everything not okay in 1 second. Now, this allows us to detect, like if we did not get a heartbeat in, say, 10 minutes, we can say, okay, the consumer is grown, let's rebalance. Remember, we don't want to rebalance spuriously too often, so we want to give it a nice, good interval. On the other hand, what if someone actually wants to leave? We don't want to take 10 minutes to decide if he already knows that he's going to leave. We want to immediately rebalance and just shorten the downtime in consuming a set of partitions. This is an interesting trade-off. On the other hand, you don't want to vote too often, and on the other hand, you want to detect as soon as possible if something went wrong so you can continue consuming. We have a bunch of rebalance timeouts and heartbeat timeouts and session timeouts that you can tune to your heart content. This is not that presentation on how to tune. And to be honest, it's not like you have very clear answers. Anyway, so if you want to leave the group and not wait for the whole detection thing, you basically go and say, hey, I am leaving the group. And the coordinator says, okay, so now I have to let everyone know and they have to rebalance. But it also responds to you and say, okay, everything is good, bye-bye. That's pretty much all it has to say, really. Okay, so we are pretty much done with how this whole consumer group protocol works. One more thing, rebalancing, because this is the essential concept here. So when do we rebalance? When do we shuffle partitions around? We shuffle them when it's not really a shuffle, it's reassigning, basically. We reassign when a member dies, which basically means that for a long time you didn't heartbeat, or when you say I'm leaving, or when a new member joins, or when the topic metadata changes. And you know, if you just go to Kafka and add 10 partitions to a topic, you want someone to start consuming those 10 partitions. So this will also force a rebalance. How do we discover that we need to do it? Well, remember, consumers continuously poll. They get data, they send the heartbeats, they commit offsets, etc., etc. Remember when I said that a heartbeat can have responses other than OK? Those are two responses that can be different than OK. Basically, one response. It basically says, okay, actually, very important to tell you, rebalancing is going on right now. Somebody already joined the group, and we're now waiting for everyone else to rejoin so we can reassign. And then, basically, once you discover that you are in the middle of a rebalance, you basically have one thing to do. You have to stop everything else you're doing. Stop consuming, stop fetching, stop committing offsets. God, don't commit offsets when you know that you already lost the partitions that you now have and someone else may be already on the way to start processing them. Definitely a bad time to commit offsets. Just stop everything, rejoin the group, think again, and get your new assignment. Now, obviously, all these protocols that I described is described in an interface. So we have abstract coordinator, and there is the parts that it implements for you and the parts that you have to implement if you decide to override this coordinator. If the examples that I talked about is basically abstract coordinator plus consumer coordinator, and this is all, it's called coordinator, but it really runs on the client side. The thing that actually is what I called coordinator the entire time and runs on the broker side, it's called group coordinator, which does not inherit from abstract coordinator. I hope this was incredibly clear, did not confuse me at all, even for a second. So I want to write my own client that participates in this coordination loop. And in order to do that, I have to implement an abstract coordinator. And the things I have to implement is basically my protocol type, which has to be unique. I have to define my own metadata. In the case of consumer coordinator, it was the topics and partitions. I may have my own resource to assign. I'll show you a bunch of examples. And then I have to implement 3 methods. What to do before join, usually just clean up a lot of state. What to do, what does an assignment look like, which is the thing that the leader will run between the join and the sync. How do I take this entire list of resources, an entire list of members, and start assigning one to each? And that's the big one. That's the one I'll keep describing over and over again. And then what to do when join completes, which is normally start working more or less. So note that you don't have to implement heartbeat. It looks the same to everyone. You don't have to implement live. You don't have to implement find coordinator. You could. No, I don't think any of them are final, but why? OK, so let's use that and elect a leader. That's kind of a nice basic example. And for that, we have a schema registry. And the schema registry basically has two. Schema registry is used to maintain metadata for topics, kind of thing. You don't really have to know what it is. It supports two operations. You can read a schema, and you can do it from any schema registry workers that you have around, or you can write a new schema. And in order to maintain consistency, you have to do it at a schema registry leader. And if you try to write a schema to a non-leader, you get back, no, you should talk to that leader. And the way we did it, well, we implemented the protocol. So our protocol is called SR, Schema Registry. And the resource we assign now is no longer a list of topics and partitions. We send in our identity. Basically, this is my URL, host and port, and I'm eligible, or maybe not eligible, to become a leader. And then the first thing that you do after joining a group is that you get back a leader. So, because that's what the coordinator returns. Remember, he selects a leader. So we have a leader. Are we done yet? No, we are not done yet, because this is the leader that was selected by the coordinator that knows nothing about our protocol, that includes the idea of whether or not you are allowed to be a leader. So we have to redo the after we have a leader, the leader has to actually select the leader. So the way the leader selects the leader is basically take all the identities that are eligible to become a leader, sort them lexicographically, and pick the first one, which means that if you have, a super powerful schema registry host and you want it to always become a leader, pick a host name like AAAA _ schema registry host, and it will always be the leader, unless it's gone. And then basically the leader sends the same assignment for everyone, which is the identity of the leader. Everyone compares the identity of the leader to their own identity. If it's the same, I'm the leader. Not the same, I now know who to forward the right requests to. Woohoo! Fantastic. I forgot to mention one important part. Abstract coordinator, which I just explained how fun it is to override, is not actually a formal part of the public API of Apache Kafka, which means that theoretically we could change it. We did not change it in the last 2 years, but we could. So if you want to just do something like partition assignment in a very smart way and not try to override something that may be slightly dangerous, you could just implement your own assigner. And it turns out that this is what we did for Kafka streams. And it turns out that you can do actually a lot of logic by just implementing the assigner logic. So the one thing the streams have to do is join 2 streams of events. And basically, the things that we want to do, if you have 2 topics and you need to join them, you want the same partition from the same topic, from 2 different topics, to end up talking to the same task. Otherwise, it couldn't really join them. And this task is going to have a state. It's going to have a RocksDB that sits on one machine. And while we can recreate this RocksDB from scratch if we have to, it's not 100% stateful, it costs time. So we don't want to. If the RocksDB state already exists, we want to assign 2 partitions to a task to a machine at the same time to do our job. Which means that in order to implement the streaming as partition assigner, the metadata has to include information about tasks, about hosts, about RocksDBs, and all kinds of fun stuff, in addition to the topic and partitions that everyone has. We call this user metadata, which is an open loophole in the partition assignment protocol. So basically, the partition assigner does a lot of work. It validates that both topics have an equal number of partitions. Otherwise, it will be really hard to parse them correctly. We validate that it groups the partitions. It creates the tasks that have to process them. It assigns the tasks to consumers and to hosts in order that, based on the availability of RocksDB. And then it sends back all this information in an assignment. Like those are the partitions, those are tasks are active, you run those tasks with those partitions, and here's a mapping to this host. If you're this host, run this stuff. So this is you can do, it turns out that the user metadata loophole allows you to do incredibly sophisticated stuff without actually inventing your own protocol. And the last thing we may want to do is assign tasks. So Kafka Connect basically has the idea that you want to connect to a database and starts reading data. And any connector could have a lot of tasks that do it. And we have different worker processes. And you want to tell this worker to run those tasks and the other worker to run the other tasks. This time, our metadata is how many tasks do we have, what is the configuration, and should each task actually run or not. So fairly simple. The leader in this case is just the leader that coordinator selected, which is absolutely fine. And it basically does a kind of a slightly modified round robin. You get this task, you get this task. There's actually, we do it twice because we have two classes of tasks, lightweight and heavyweight, but that's the main idea. So, to summarize, Kafka has a pretty generic coordination protocol. And you can use it to assign partitions in a very nice generic way, and you can cheat with cool user metadata. And then you can also override the entire assignment protocol to actually assign things that are not partitions at all, that are leaders and tasks and database partitions and producers and all kinds of things that are kind of unrelated. So we really want, first of all, I would love more people to use it. I feel like doing leader elections that way, for example, is often easier for me to do than it would be in Zookeeper. If you do, definitely let me know. Drop me a line or drop the Kafka user group, developer group a line. We need to know, because if you use it, we may decide to make the API public so nobody else will, so we wouldn't change it accidentally on you. So we really have to know if someone who is not us is using it. We have some future plans to use things like generation ID. There already is a generation ID in the protocol, so you know if the assignment changes, it has a different ID. You can use it to do all kinds of fencing things, which we currently don't do, but it would be nifty if we did it. We could do things like, remember, the clients control what to do when they get rebalance in progress. So they can, right now they basically stop consuming completely. But if you know that you're using something that is sticky, you could keep on processing knowing that you're not going to lose your partition. So we can get a lot smarter with that. And then the last thing, right now, it's everyone, if a new consumer joins, everyone rebalances. Why? I mean, if we only move some partitions from some members, why should we tell everyone that rebalance is going on and have everyone join? That's kind of a big operation. Why not have an incremental rebalance? So those are all things that we're looking to improve. And then if you want some reading material for the flight back home, you can read more about offsets. You can read a design that coordinates in the broker, which we decided not to implement. You can read everything that I basically just said, like the first half of the talk, in long written format. And then this is the example in the Schema Registry if you want to go and see. It's really very, very few lines of code that give you leader election, because most of it is in the abstract coordinator implementation. Do I have time for questions? How are we on time? We have 3 minutes, right? That would be like 1 or 2 questions. Anyone has questions? I totally overwhelmed everyone. Yes? Oh, the offset thing? We basically, it's a very well-known pattern from relational databases. Like, we knew it from Oracle redo logs and MySQL bin logs, basically. You have a sequence number. I think the big idea was applying it to something that was at the time more or less a pub-sub messaging system. So, and yeah, and if you're interested in that topic in general, the book I Love Logs by Jay Krebs is literally changed my life. Like, I read that and I'm like, oh my God, this is brilliant, and switched careers to work on Kafka. I'm not even slightly exaggerating. Yes, someone in the back. Yep. The group protocol does not maintain consumer lag because offsets are kept on a topic in Kafka, but there is a bunch of tools that will basically check the topic periodically and tell you how far behind consumers are. A nice open source one would be Burrow. A graphical a proprietary one would be the Confluent Control Center, and you can basically, yeah, I don't know. And it's kind of easy to write them yourself. I mean, there is a documented format for how those things get committed. One last question. Yes, the guy with a bird. Oh, how big is it going to be? So Kafka limits the request size, and it's limited by default to 1 megabyte, which is way, way, way too large, and please don't ever get anywhere near that. You may, I mean, if you don't know that you have that, maybe drop it down to the reasonable 20K limits. But yeah, I mean, that's basically the request size limit is the limit that you're looking at. I'm out of time, and I actually have to run to the airport. I am a Strudel Gwen Shap on Twitter, and I'm incredibly happy to answer questions on Twitter, so you can go for it.